Okay. So thank you to the organizers, because we've been workshopping this paper for a while now, and it's a great opportunity for us to actually present our Drei-Menschen-Arbeit about the Drei-Männer-Arbeit with some of our targets in the audience. So that's good fun. So yes, we'll be talking not about the entire three-man paper from 1926, but just Jordan's derivation of blackbody fluctuations. So my job is to set the stage, and then these fine young fellows here will take home the lesson. So as you're all well aware, in 1926, Born, Heisenberg, and Jordan published their three-man paper in which they give a first definitive form to Heisenberg's matrix mechanics. And one of the most interesting aspects of this very interesting and dense paper is Jordan's derivation of Einstein's 1909 formula for blackbody fluctuations. So just to jog your memories, in 1909, what Einstein had done is shown that the mean square fluctuation of the energy of radiation in a subvolume and in a small frequency range of a blackbody is this equation here. But what you'll notice is that we have a particle term here with our quantization unit there, and a wave term here. And Einstein sort of shrugged and said, well, this is a kind of fusion of the wave theory and the emission theory. So you have both particle and light, wave light in this one equation. But what's really fascinating about Jordan's proof is not only that he derives this equation using matrix mechanics, but that using this singular framework, okay, he gets both the particle term and the wave term out. So it's not just a smashing together of these two different theories as Einstein sort of perceived it, but it's the emergence of both of these terms from within matrix mechanics. So Jordan's derivation yields these fluctuations using a matrix mechanical treatment of the wave field, and he uses for this Ehrenfest's one-dimensional example of a string that's tied at two ends. And so what he's actually doing here, and as Michelle and Tony do a really nice job of writing, giving the overview for in their 2008 paper, is he's calculating the quantum uncertainty of the energy in sort of a subsystem of this string, and that subsystem is assumed to be in an energy eigenstate of the whole string. So just like in other attempts to quantize, in some ways, Jordan was assuming uncoupled harmonic oscillators were representing the different energy modes of the string. Okay, so he carries out his proof, and voila, gets this amazing, recaptures Einstein's equation, but again, all from within matrix mechanics. And Jordan's proof is unlike Debye's and others' attempts to quantize fields, because those attempts were partially successful in that they recovered the Planck formula, but they couldn't get the fluctuations aspect correct. Okay. And this is something that Ehrenfest emphasizes in his 1925 paper, and Owen will say a bit more about that. So again, as I said, it doesn't, Jordan's proof doesn't require this introduction of the hypothesis of a light quanta by hand. It comes out. Okay. So in Duncan and Janssen's 2008 paper, and there's the full title there, you guys presented this at HQ2, right? Yeah, okay, so this is from a previous such conference. So Duncan and Janssen discussed the significance and the reception, or the stunning lack thereof, in some of attention to Jordan's result, because it provides the definitive resolution of this wave-particle conundrum. It's this really important result. And it's, interestingly, and as Laval has pointed out in his very nice paper, that it's the starting point for sort of quantization of fields. So it's important in all these respects. But what they focus on in their paper, Duncan and Janssen, is Jordan's derivation and how there are various problems with it, i.e. how it might give rise to supposed infinities and why that was not a fair critique of what Jordan was doing, and other things like that. But importantly, Tony and Michel say that the proof that Jordan is doing is incomplete because Jordan fails to consider thermal ensembles, right? So what we're really thinking about when we're deriving the Einstein fluctuation equation is looking at such subsystems and their energy eigenstate, but averaged over the whole ensemble, and that's not what Jordan is doing. So what we're up to here is, in the part that Owen will give, we're going to sketch how we think Jordan's derivation sits really nicely within a Boltzmannian framework. And even furthermore, we're going to say that this Boltzmannian framework implies something about Born, Heisenberg, and Jordan's interpretation of matrix mechanics, and in particular of energy states. And that when we reread Jordan's proof in this Boltzmannian way, not only is it already complete in that context, but it tells us a little bit about their conception of matrix mechanics from a more philosophical perspective. So, wait, we're going to do this seamlessly, so begin now.
Okay, so I'm going to be talking about the statistical mechanical side of things, and particularly the kind of Boltzmannian account of thermal fluctuations. Now I'm going to use Boltzmannian and Gibbsian in a sense as in the kind of the way we use it in a modern way of dividing of approaches to statistical mechanics, rather than in a sense that these were words that weren't actually used in this sense at the time. But that there certainly was, and Ehrenfest was particularly responsible for this, an understanding that there were these two different ways of doing statistical mechanics. So one of the things when you read the Jordan's derivation of thermal fluctuations that might seem perplexing to a kind of modern eye is that he makes seemingly no use of thermal properties for the system, and yet seems to get out a spectrum of thermal fluctuations. And this is one of the things that I think is actually pointed to in Duncan and Jansen's paper, and they say you need to actually put a thermal ensemble over Jordan's derivation in order to make this actually proper a thermal spectrum. However, I think that if you actually look at the derivation in the context of the sort of the Boltzmannian approach to statistical mechanics, that this actually can be understood as how you get these thermal fluctuations out without actually putting a thermal ensemble on the entire system. So to sort of recap that, I'll give a sort of very familiar account of the Boltzmannian account of thermal fluctuations in a gas, and this appears in all the undergraduate textbooks. It's fairly straightforward. So you start off with a box containing a gas, very, very large number of molecules, which are all bouncing around in this box, and then you pick a cell, which was going to be in a very narrow region, so it's a narrow space, but also a very narrow band of momenta. So it's specifically looking at the molecules that are bouncing around that are in this particular area at this point in time that lie within also a narrow band of momentum. So the center on it is on some position and some momentum. And then the total energy in that cell is actually given just by roughly the number of molecules within that cell multiplied by their individual energies. And then, with the various sort of phase-space type arguments, you come up with a most likely distribution for these molecules, and here it is. And it turns out to have this kind of form. And it gives the Maxwell-Boltzmann equilibrium distribution. And that is the most likely distribution. It's the one that occupies the largest volume in the phase space. Interestingly, temperature, of course, plays no explicit role in this. It essentially is derived, in a sense. If you actually then consider this gas to be an ideal gas and obeys the ideal gas law, you find that you can actually identify the temperature with this parameter here. Now, if we pick this cell out, this cell is kind of a little bit fictitious. There's no wall surrounding it, so the atoms are just bouncing around, and we just happen to be looking at this particular region at a time. And the atoms are moving in and out of this box all the time. So there's thermal fluctuations going on within this cell, corresponding to the exchange of particles between the cells. Okay, so that was kind of like undergraduate textbooks. Now we can do the same thing with waves. So here we imagine a box containing some black-body radiation. So it's a large oscillating field with lots and lots of high-frequency vibrations, and we're specifically looking at very high frequencies compared to the side of the box. So now what we would do is we would take a cell, which, again, we look at some particular region, and we look at a narrow frequency band. So we just look at the oscillations within, centered on some position with a particular frequency of oscillation. And if you look about, well, how much energy is in that cell, it's going to give you this term, where the energy depends upon the amplitude of the oscillations. So the next stage in the treatment is to actually assume that each cell can be treated as an independent oscillator, and that the energy in that cell depends upon the amplitude of the vibrations on the oscillations. And thermal fluctuations, in this case, because of the fact that, again, there are no walls around this cell, there's actually lots of oscillations going on. So the oscillations are actually very, very high frequency and moving around a lot. So there's a lot, and they will be moving in and out of this particular cell at any given frequency. So again, you've got now thermal fluctuations corresponding to the exchange of energy between cells. And classically, if you then try and derive a most likely distribution, you're going to end up with the Rayleigh-Jeans law. So we've actually got a very straightforward sort of parallel situation going on here. The particles give you a cell where you're centered on a position of momentum, and for waves, you center on position and frequency. The occupation number is given by the number of particles in particles, and the amplitude of the oscillation for waves. There's an equilibrium distribution, Maxwell, Boltzmann, or Rayleigh-Jeans. It's not strictly an equilibrium in the case of Rayleigh-Jeans. It's a most likely distribution, would be a better way of putting it. But thermal fluctuations are observed within this cell from either an exchange of particles or the exchange of energy because of the oscillations moving around. In both cases, what we've got is, in the Boltzmannian view, a large system that's in a definite state, but typically leading to a small subsystems undergoing thermal fluctuations with this very thermal character. The temperature of the subsystem gets derived from the properties of the much larger system, but you don't need to put the much larger system into a thermal state itself. Well, why is this wave picture, why doesn't this appear in the textbooks? Well, the answer, I'm sure, is we all know in this room. The reason why this wave picture doesn't appear in undergraduate textbooks is because it has a slight problem. Called, indeed, by, I believe, Ehrenfest, the ultraviolet catastrophe. And the problem being that there's just too much energy in the low, even in low amplitude, in high-frequency vibrations. And the solution, again, as we all know, is given by saying, well, actually, yeah, this isn't what we want. What we want is something to do with Planck's law. And we have to get Planck's law out. Now, I mean, there's a whole history of the different derivations of Planck's law. But the problem then becomes the funny fact that gets noticed that when Einstein takes the black-body spectrum and he derives these two terms, he gets a photon term and he gets a wave term. But the various attempts to actually derive Planck's law, say following biquantization, failed to get the photon term. They were all coming out with just the wave term. So the overall distribution was being governed by Planck's law, but the thermal fluctuation spectrum of the region was coming out with the fluctuation spectrum associated with the Rayleigh-Jeans law. Now, Bose, and introducing Bose statistics, abandoned statistical independence of oscillators as one way of doing it. There's a very key paper by Ehrenfest, which really emphasizes the problem here and shows how using biquantization, you can reproduce this Planck equilibrium law, but paradoxically, you get the Rayleigh-Jeans spectrum of thermal fluctuations. So it's not just enough to introduce some sort of a quantization procedure. You're still not getting the wave-particle duality. So we get to matrix mechanics. And so Jordan essentially follows exactly the pattern that we've just done, only now, instead of having a classical oscillator with biquantization, takes a classical oscillator and replaces them with matrices. And it follows through, and the triumphant result is that with this situation, he gets out the wave and the particle term. So at that point, it's looking very good from the Boltzmannian point of view, you'd think. It's Okay, so we can accept that it doesn't have to be an overall thermal state because the Boltzmannian point of view says pick out a subvolume and you get thermal fluctuations from the subvolume. But the argument for that was that you've got exchange of energy going on between the individual subvolumes. And the problem is, when you're looking at the quantum state now, does this actually make any sense anymore? Because now you've got the whole system is just in a single quantum state, and that's a stationary state, and now how can there be exchange of energy going on between the subvolumes if the whole thing is just in a stationary state? So even though the Boltzmannian point of view seems to be answering some of the problems, it's not going to be enough. And now I'm handing over to Guido.
Okie dokie. So that's a problem. So we've got Jordan's derivation using matrix mechanics formally seems to give us the correct result, but the question is whether it's really giving us thermal fluctuations. From a modern point of view, knowing modern quantum mechanics, Jordan has been doing is calculating the quantum spread of the energy in a segment of this string. I mean, his model is really a one-dimensional string, standing in for the cell in the gas. If indeed the whole string is in a definite energy state, the segment is not going to have a well-defined state. In modern terms, it's going to have some reduced state, and of course, as Christoph pointed out to us once we gave a version of this talk in Berlin, of course, if you've got the reduced state, you can that tells you anything you can measure about that system locally, but that can't be what Jordan meant either, because the modern notion of state had not been introduced at this time. So, one way out, as Tony and Michel have done, is to look at a thermal ensemble, and then it's clear how the result makes sense. But we want to argue that even without doing that, by looking at how Jordan thought of matrix mechanics, the interpretation of matrix mechanics at this time, you can make sense of the result in Boltzmannian terms. So what you need is the idea of an exchange of energy between these subvolumes. Okay. Right. Again, to rehash the very familiar, what we've got in matrix mechanics, instead of looking at Fourier series, we have these quadratic arrays, and these arrays or matrices are going to be solutions to the classical equations of motion under the additional quantum conditions. Now, what was the original interpretation of matrix mechanics? Claim the way Born, Heisenberg, and Jordan understood the theory was like this. A system, a matrix mechanical system, is always in a stationary state. This is sort of Bohr's fundamental postulate. A system is always in a stationary state. But in general, it's going to be performing quantum jumps between these stationary states, and the new ij's are the transition frequencies, and by solving the equations and so on, you get lots of good things coming out of the formalism. But strictly speaking, if you have an isolated system, it is in a stationary state and it's not doing anything, just sits in that stationary state. Yeah. A little later, 1927, Born and Heisenberg put this problem very pithily. The most noticeable defect of the original matrix mechanics consists in the fact that at first it appears to give information not about actual phenomena, but rather only about possible states and processes. It says nothing about when a given state is present or when a change is to be expected. In order to have true processes, as long as one remains in the domain of matrix mechanics, one must direct one's attention to a part of the system. This is no longer closed and enters into interaction with the rest of the system. And this is already looking encouraging. Here's the subvolume or subsegment of the string. They're going to focus on the segment of the string, and something interesting is going to happen. Now, again, this is sort of 1927. I'll first say how, at least at this stage, it's clear what Heisenberg and Jordan think about this problem, how this defect can be fixed, and at the very end, I'll just point to evidence that this was the original understanding as well. So these two papers are almost exactly contemporary. What do Heisenberg and Jordan do? They consider two weakly coupled systems with at least one energy difference in common, so there's going to be resonance behavior between the two. And if you look at the energy matrices of the subsystems, because of the coupling, they are not going to be diagonal in the same basis in which the energy matrix of the total system is diagonal. So they're not diagonal in the energy basis of the composite. That makes them time dependent, and what you have is a sort of slow exchange of energy between the two. And what Heisenberg and Jordan show explicitly, or trying to argue in these papers, is that this result can be interpreted in terms of quantum jumps in the subsystems, sort of correlated quantum jumps. This system jumps up when this system jumps down, and vice versa, and the two systems are exchanging quanta of energy. Yes. Now, if that's the picture of matrix mechanics of subsystems, that's exactly the ingredient that one needs in order to make sense of the Boltzmannian derivation. We had formal result, which was fine, but the conceptual ingredient that's needed in the Boltzmannian scheme in order to have thermal fluctuations is energy moving in and out of the cells. And this is what supplies energy moving in and out of the cells. Right. Last element of the puzzle, is this really what Jordan had in mind at the time of the Dreimeiner Arbeit, or is this sort of an afterthought from 1927? I mean, it's clear that in 1927, November 1926, that's the way they thought. Can we project that back? Is there evidence for that? Or is it just sort of indirect evidence that this is what Jordan must have had in mind? Yes, I mean, there is evidence. This is the closest we get to the smoking gun. This is Heisenberg in this little fluctuation paper commenting on the Dreimeiner Arbeit. And he says, as an example of what he's doing, in the end, one can give the way the calculations by Born, Jordan, and the author and Heisenberg about oscillations in a crystal lattice are contained in the considerations developed here. It is energy oscillations in a small subvolume of the crystal. Okay, only sort of confusing point is why is he talking about a crystal rather than sort of blackbody radiation? That's in a sense that's a detail. There was some discussion whether the calculation really applied to radiation. I mean, the model is actually a one-dimensional string, so it's much closer to the sort of crystal lattice. It's sort of vibrations in a medium, rather than the electromagnetic field. So it's, Heisenberg was very confident that this worked for the crystal lattice and was not so bothered about whether it was really applicable also to the radiation field. Jordan was bothered, Heisenberg wasn't so much, but that's secondary to the conceptual point we want to make. However we interpret the scope of Jordan's calculation, this is the way to interpret it. And in fact, tellingly, in the little note on fluctuations, this exchange of energy quanta that Heisenberg has, he talks about the quanta being exchanged as sound quanta, as in the crystal lattice. It's vibrational energy that's being exchanged. That's it. So two ingredients to make sense of Jordan's formal derivation. One is the Boltzmannian point of view, and the other one is the interpretation of matrix mechanics that gives us the exchange of energy between the cells. Thank you very much. Yeah, maybe we should.
Start with the first three, because that's my memory maximum.
All right. Well, good thing we're not both sharing this session, because. So I wanted to invite you to comment on this. Well,
I'll say a few things.
Okay, so so let me first say that I'm very sympathetic to the project. When you first told me that, look, there is a way to make sense of this, that where you just use the Boltzmannian rather than the Gibbsian way, I thought this is great, right? Because clearly, like Jordan gets it from Ehrenfest gets it from Boltzmann. This looks very promising. So now, but I have some problems with the details. So on Owen's part, right? So when you were talking about and what Guido, what you were saying at the end about the connection between the crystal lattice and the black, and what you said about like it's the same thing. That is, granted. I mean, like we have no beef about that. But when you're talking about these oscillators, it sounded as if you were what replaces the cells are like sort of localized oscillators, whereas these oscillators, the way we understand the calculation, are not localized at all. They're Fourier modes, right, that live across the entire string. And so one of the things that you guys puzzle about, how can there be energy going in and out of these volumes? That is not something that is a puzzle for us at all. Because like you just look at a segment of the string, and for every energy mode, right, that is going to live along the entire length of the string. And, like some of the energy in that mode is going to be localized in that little segment, and other part of it is going to be localized outside. So, so this is my first question. Are we interpreting these oscillators differently? And if so, like, is there textual evidence to decide this? I mean, like, I thought that Tony and I had understood correctly that these oscillators are the things that live across the entire string. So a few other I'll try not to go on too long. A few historical questions, right? So one of the things that puzzled us, and that again made me sympathetic to the project, is that like you can say that, well, Jordan didn't quite do this last step because this theory is very new. Like who can blame him? Okay, but the calculation is similar in the classical case, and so Lorentz does this in the classical case, and he also does not take a thermal ensemble average, okay? And so, right, so this is like the 16, you know what I'm talking about? Right, so the Lorentz calculation, just at the classical case, Lorentz does not take like an ensemble average. We do that, and then you get, you know, just the analog of the Rayleigh-Jeans law, right? Now, so my puzzle now is, so in the Boltzmann approach should also make sense of that. But then you don't have this other ingredient of like, you know, this funny interpretation of these Resonanzerscheinungen. Right? And that can be then finally to my last question. So is the claim that this reconstruction is kosher from a modern point of view? Because like, you know, this whole thing about the Resonanzerscheinungen sounds to me like kind of a sort of intermediate step in coming to the proper interpretation of quantum mechanics, which is not developed until later in 27. And I'll shut up.
Shall I? I mean, I've got answers to 2 and 3, I think. I mean, let's start. Yeah, I think 1 was more for you, but so answer to 3. I mean, this is not about sort of what's kosher from the modern point of view. It's really about trying to make sense of what Jordan was thinking. And with 2, in the Lorentz case, I think there is no mystery about energy coming in and out of the cells because it is all classical. Yeah, classically, that's the picture that we have. Energy coming in and out of the cells. The question that we were puzzling about was, okay, quantum mechanically, or matrix mechanically, okay, I mean, what plays the role of the energy being exchanged between the cells, and it's the
question: how do you interpret these oscillators? My first question.
Yeah, that's probably right. Is this working? Yeah. Okay. So I believe that, I mean, the calculation that's actually performed is looking at a particular narrow section of the string. That's true. And so it is looking at energy within the string. Now there is something a little bit puzzling about this, because obviously if you've got the one string, then you just want to take whatever normal modes that is and just Fourier analyze it, and then you just found that each mode is on the whole string. But of course, if you actually look at what they're actually talking about in the situation, you've got a situation where it's not, you know, your violin string, where it's just at these very low frequency modes. We're talking about very, very high frequency modes. So the string is actually like oscillating with very complicated patterns all moving up and down the string. So, you know, it's not actually this nice visual image of it's just a single mode oscillating across the whole, with the whole string vibrating. So for that one, if you actually had some little solution, a traveling wave, say moving backwards and forwards, you would want to describe that to some extent as the energy all being confined in one region of the string. And you might want to then look at that and try and Fourier analyze what's going on in the string, but you don't actually going to have the boundary conditions holding them tight on either side. So it's going to be a little bit more tricky. Yeah, does that?
That's a problem for you.
Yeah.
It's pretty clear from what Jordan is doing that when he talks about you can replace the string by a set of uncoupled oscillators, that what he means is like, you know, that you have all these modes and they go up to very high frequencies. So I totally agree with you that he looked at very high frequencies, right? But I think the picture doesn't change. So like if you say like, well, you can also think about this differently, then, you know, like you need to say like, and that sort of must have been in the back of Jordan's mind, because that's not explicitly in the text.
Okay, we had this stuff over here. You got up there? Yeah. Okay. So this is right to this point. I think that point was not a problem for Jordan or anybody else, because Ehrenfest had very nicely and intuitively explained that, right? That if you have this sum of all these independent modes of the whole string, what you get is local beats, right, that move around. So yes, classically, you have this perfectly consistent picture. You have a stationary distribution of energy over those modes, but locally, right, you have, because of the local changing interference, you have like sometimes locally it moves more and locally it moves less, right? And Ehrenfest says something like it breathes in and out energy because of the beats between the different modes. And so you don't need localized waves that have some like x coordinates, right? All you need is really the independent modes of the whole string. But about the Boltzmannian picture, I would like to ask something, because I mean, might come back to Michel and Tony's argument always was starting out from the Gibbsian picture, and I think that works just as well, and I think that also helps to understand why it works just as well for Lorentz on the classical account, right? That already on the classical account, of course, what you can say in exactly this image that Ehrenfest is saying, right? You have a microcanonical state of the total system, right? In the total system, nothing is happening. It's a perfectly stationary state, right? The distribution of energy over the various modes is absolutely constant. But that microcanonically defined unique state produces on the subsystem a canonical state, right? That's how Gibbs actually introduces canonical states, right? As the states of subsystems of a big system that is in a microcanonical state. And that subsystem is in a canonical state, i.e. has a temperature, has a thermal distribution.
Which temperature? Which temperature?
The temperature that you derive in exactly that way.
There is no temperature in the result of
So
there is no temperature.
You could just as well.
No, there is no temperature.
You don't need a temperature. You don't.
But you said that somehow you were inevitably led to a distribution of fluctuations in a so-called characteristic of a system at some temperature.
Yeah.
What temperature?
Which is given by the energy of the total system distributed over all of the subsystems.
I can subject what the order does to a thermal average at a number of different temperatures.
if I may.
You then you get different energy.
So-
There is a certain conflict which I will abjure from any further conflict.
So, I mean, one of the interesting things about the Einstein thermal fluctuation thing is that because the way it's expressed, temperature doesn't actually appear in it. So it's supposed to be a thermal fluctuation spectrum, but it doesn't actually have an explicit temperature in it. So so that fluctuation spectrum would hold for any temperature.
What's more, not just for any temperature, but for what we show in our paper is that for any sharp state of the full string, where the excitation quantum numbers of each mode as a function of frequency is a smooth function of frequency, not necessarily that function corresponding to the Planck law, but any smooth function of frequency, the fluctuation result will hold.
Okay.
And all of those functions that don't follow the Planck form do not correspond to any particular temperature.
So I'll
Let's see.
You're being a naughty chair.
I am being a naughty here. Let's see. We do have six more minutes.
So this is, I mean, Michel already asked my question basically about the localized oscillators in the cells, but maybe I can. It seems to me that the implication of phrasing it that way is that in somehow Jordan would be introducing dynamical variables that are localized in that cell. But he never does that, right? I mean, he just looks at the partial Hamiltonian for the cell, and that's all he needs to do. And the partial Hamiltonian is still defined in terms of the dynamical variables of the overall system, which are, of course, the the Fourier coefficient of the mode. So I'm wondering, what does that formulation of saying that you can consider the cells as individual oscillators actually do for you? Why do you need to even make that? And yeah.
Yeah, I'm not entirely sure what the... I'm not really quite sure what the question is getting at.
Why that formulation that Michel objected to of interpreting the cells as localized oscillators? Because it seems, I mean, it's not something that Jordan explicitly does, nor do I see how it's necessary for your interpretation.
So, I mean, I think the point actually, I'm feeling the response is the same as actually I think Christoph is saying, is that this is the idea is that you've got these actually sort of oscillations going on, that you can look at the energy being localized in particular places.
Look at the energy being localized, but I wonder why the formulation in terms of looking at the cells as localized oscillators, because that implied, and that's how I understood Michel's criticism as saying that...
The cells aren't the localized oscillators, right? You just have...
You take a region of space and
you just look at the localization of the energy in those cells.
Yeah.
But your formulation was very misleading in that sense, and I think also that's what brought Michel to object. Yeah, okay, go.
This part.
Go.
okay.
No, the xi is fine. I mean, the energy is going to be localized, but if you go a bit further, or is that... well, you just said it in words, right? Then, no, each cell can be treated as an independent oscillator. I'm not quite sure what that means or what it does for you.
Right.
Why is it an oscillator?
So the...
An independent of what?
Right. So if you look at the Hamiltonian, the idea is that each cell is an independent oscillator is actually treated as being an independent of the oscillations at the same frequency in the next cell over. That's what the independence is about. So you've got. So this is one of the contrasts with the Bose approach, where that independence is actually what goes.
No, but there it's the independence between the different modes, not between different cells. I mean,
Yeah.
But I mean, obviously the cell can't be independent of what's happening in the rest, otherwise energy wouldn't go back and forth between them, right?
Yeah, it's an imaginary. Yeah, there are no real boundaries in the cell.
Yeah.
It's right.
Well, then isn't it independent? I mean, I just this sentence seems to be superfluous and wrong.
Okay.
Thanks.
Fancy put. Yeah.
I have to think about that.
Yeah. I think that. I'd
No,
actually
fair
say I
enough.
think that's interesting feedback, and I think I would actually like to think about that.
This is more a question for Christoph than for you. So if I understand you correctly, then you would say that they also don't need this song and dance about the later interpretation. It's all already there, like in just following your notes and doing Boltzmann. Am I understanding that correctly?
There is something to be said about, and that I think is correct, how they interpret these, of course, from a modern quantum mechanical point of view, right, there is a problem in saying that quantum mechanical spread of states is a thermal spread of states. And there I think they do have a point that I just, as a historical point, I'm a little bit skeptical about the retro projection, even if Heisenberg makes that claim, because of course, at least in the case of Heisenberg, it's pretty clear that he developed this argument as a response to Schrödinger's argument about the beats and wave mechanics, right?
Okay. But now you're being naughty because you're not answering my question anymore. So you have to wait till the microphone cycles back to you.
No, I thought it was the other way around. Schrödinger was replying to
question, but I'm not quite sure about the second question.
Thanks. That's